This is chapter 26, and I was working the last thing with Kirchhoff's. I want to start with Kirchhoff's law or rules. Here, for Kirchhoff's laws or rules, we are going to have networks that cannot be reduced to simple series and parallel combinations, and therefore we need to analyze these networks using techniques developed by a scientist. His name is Kirchhoff. Now, what we need here to know, we need to know that there is something called loop, and that loop is going to have junctions. Here we have A, C is a junction, B is a junction, A is a junction, B is a junction, D is not, it's just, it has one route, and C also, it has one route. Now you can see that I can, usually I will give like a letters here, then I can say A, let's say E, C, B, then this is how I like maybe to do it. And then when I will say I'm gonna sweep the circuit, E, C, B, A, E, I'm going in this direction, which is written here. Also, like like I can have a loop 1, which is the external one here for all. I can have loop 2, which is the one on the left. I can have loop 3, which is on the right. Now, the junction here, it is where we have branches of current. The current is gonna branch. Then you might have I1 that is gonna go into like to split into two. Then I will say I1 equals I2 plus I3. We're gonna see that. And here, something that we need to know, that a junction is a point where three or more conductors meet. Conductors here, I'm talking about wires. And we say here the sum of the currents into any junction equals 0, which means the sigma n equals sigma out. Here, for example, I have I1 going into the junction, I2 going into the junction, and then in that branch here, we're going to have I1 plus I2. Very similar to water pipe, where you're going to have some of the water flowing here through this part and this one through this part, and then therefore they're gonna both going through this way here. There is another rule, we call it Kirchhoff's loop rule, and it is any closed conducting path, like we did before, and that is, it is valid for any loop is, and simply it means that if you will go from point A and then you're gonna go around the loop and then go again to point A, then the sum of the potential differences is gonna be 0, because you are going back to the to the same point. The loop rule is a statement that the electrostatic force is a conservative force. Now here, sign conventions for the loop rule, and these are really important. Use these sign rules when you apply Kirchhoff's law. Then I will say when you are traveling from negative to positive through the EMF, then you are going to consider this as plus E. When you are traveling in the opposite direction from positive to negative, you are going to have it negative EMF. For resistors, if you are traveling against the current or opposite to the current direction, then the voltage, like here I will say, is going to be positive, I times R. If I'm traveling in the same direction as the current, then I have negative IR. And we're going to apply this to loops in a little bit. Also, like I can apply Kirchhoff's law or rules to a single loop circuit. And now, of course, like I can use the other technique, but it's like here we're gonna see how we're gonna use it. For example, here a circuit shown contains two batteries, each with an EMF and internal resistance. When you are using one car to charge the other, and using Kirchhoff's rules, you can find the current in the circuit and the potential difference VAB and the power output of the EMF of each battery simply by applying the rules. I'm gonna show you here for a simple circuit how we're gonna do that. Here I have in the circuit, I have the current in the 3 ohm resistor is given as unknown. I don't know it, and the other currents are given. Like for example, through R it is 2 amperes. Through the 4 resistor it is 3. Through the 6 ohms it is 5. We need to find what is really the current in the 3 ohm resistor. We need to know the unknowns EMF1 and EMF2 and also the resistor R. Now I can do the following here. I redraw the circuit, and then I said this is gonna be my direction of sweeping the circuits. And I know that also that the current is through here, this is I3 is gonna go continue here, and then when it will reach this junction is gonna go here, and also I2 it is going in that direction, and therefore when it's gonna come here, then the currents they're gonna add up here, and this is really the 3 ohm resistor. Then I can say that the current through the 3 ohm resistor is going to be 3 plus 5, which is 8. Now I can also like I will say this is loop 1 and this is loop 2 and this is loop 3. For loop 1, okay, I'm going with I'm going in that direction, which is with the current, then negative I1R, and then here I'm going from positive to negative, then it should be negative EMF1, and I'm going here from negative to positive, then it should be EM2 E2, and that equals 0. Now also I can this is okay, let me give you like different colors. This one here is gonna be loop 2, where I went through that EMF from negative to positive, then it is EMF positive E1, and then I went through this resistor here with the direction of the current, negative 4 times I2, and then I went through the 3 ohm resistor against the current, and therefore all equals 0. From this one here, I can rearrange and find that like I have all the numbers, then I will be able to calculate E1 to be 36 volts. Now also I can, this is going to be loop 3 equals 0. And from that also I can conclude that E2 is going to be 54 volts. Now I can go back to this equation here, and then I can say minus I1R minus E1 plus E2 equals 0. Now I know E1 and E2, then I will be able to calculate R as 9 ohms. Then this is really the one, like, it's not a one loop, I would say, like the easy, like it's not that complicated. Here I have another example here where I will have, this is a typical Kirchhoff's laws or rules problem, where I have resistors and an EMFs around, and I need to find the current in each branch and the potential difference VAB of point A relative to point B. Now I will say here sigma IN equals sigma I out. Therefore, I will say whenever I'm gonna go to this junction, I can say that I1, I1 is the one that is here, and I2 is the one that is here, and this is I3. Then I can say that I1 is gonna branch to I2 plus I3. And this is the first equation that I'm gonna get, which is from the current rule. Now I can consider the loops, and then here I will say the first one, it is I'm going from A, B, C, F, A. Then this is loop number 1 here, loop 1, and in that I will say E1 minus I1 R1 minus I2 R2 minus E2 minus I2 R3 minus I1 R4. I here I wrote for you what is the value of E1, what is the value of R's all. Okay, here, and then I collect the like terms, and then finally I'm gonna have this is my equation that I'm gonna use, one of the equations. I have two unknowns. Now I will now go also, this is my second loop, and here I will say I did the same thing. I'm going from F, I am going against the current, then I have I2 R3 positive, and then I'm going from negative to positive through E2, then it is plus E2 plus I2 R2, and then minus R3 R5, which is the, and then here I rearranged my values, and then finally I ended up with this equation. Now I have this equation and I have this equation here. Then I was able to substitute my values. I have two unknowns and I can solve by elimination. I did multiply here by -2, and then I added the two equations together, and finally I was able to calculate I2 as 0.20 amperes, and I can use that same equation to calculate what is really I1, and I was able to calculate I1 to be 0.8, and then finally I3, it is I1 minus I2, then it is 0.8 minus 0.2, which is 0.6. Also, we can use it to calculate the voltage, the between like two points, and here we need between A and B, and therefore I did move from, I will say VA, and here plus EMF1 minus I1 R1, and here minus I2 R2 minus 5 equals VB, and I did this here, and then finally I substituted my values, and then VAB is negative 3.2. Here we are really talking a little bit about, you know, different, let's say, measuring devices. And here we have the galvanometer, which is measuring the current that passes through it. And this is like, I would say galvanometer is different from ammeters, that it is measuring the very small currents. Ammeters and voltmeters here. The ammeter measures the current passing through it, and the voltmeter measures the potential difference across a resistor. Both instruments contain a galvanometer inside. Ammeters and voltmeters in combination. An ammeter and a voltmeter may be used together to measure resistance and power. Two ways to do this are shown below. And either way, we have to correct the reading of one instrument or the other unless the corrections are small enough to be negligible. Ohmmeters are really devices used to measure the resistance, and I will say now we are using what is called multimeters, which they can use, which can be actually used to do more than one job. Potentiometers are really variable resistors where they are going to, have a resistor that is not having a constant value. It is having, different values. It seems that one of my slides is been moved. Okay, let me get it back. This one should be number 3 here. Okay, now here, charging a capacitor, we have here a simple RC circuit. RC circuit means resistor and capacitor. We're going to do an experiment related to that. We idealize the battery to have a constant EMF and 0 internal resistance. And we begin with the capacitor initially uncharged and the switch is open. At some time, we close the switch, and then the current is gonna start, is gonna initiate it in the circuit, and then the capacitor is gonna start charging. The charge on the capacitor, it increases exponentially with a time constant equals RC. Now we can say here Q, it is C, the capacitance, times the EMF times 1 minus E minus T over RC, which is a Q final 1 minus E minus T over RC. Also, after we are disconnecting, we can have, this is, we can have the discharge. But okay, now we can see also that the current is gonna start during the charging. We're gonna have the current starting very big, and then it's gonna decrease, and the current here is gonna be also having a time constant of RC. I, which is dQ over dt, is going to be EMF over R, E times minus T over RC, or I0 E minus T over RC. Then it's going to decrease exponentially. Now I can discharge the capacitor. Now the capacitor is having a charge, and the current is 0, and then when I will close the switch, I will allow the capacitor to discharge without a battery, of course, through the resistor, and as T increases, the magnitude of the current decreases while the charge also decreases. And this is really, we're gonna have the discharge. Q is gonna decrease exponentially, and also for the current here is going to be decreasing exponentially with a time constant RC, and here it is the equation for discharging. Here we know that shows the basic idea of house wiring, where we have the hotline has an alternating sinusoidal. This means like it's sine wave with a root mean square value of 120 here in the United States volts. The neutral line is connected to ground, which is usually an electron that is driven into the earth. We use also, some of the tools for, for safety, like the fuse and the circuit breakers. Okay, and here is the last one, which is I have an RC circuit, and here I have both capacitors are initially charged to 45, then this is a discharge. How long after closing the switch S will the potential across each capacitor be reduced to 10 volts? Here I need to find what is really the equivalent resistance and what is really the equivalent capacitance. And here I have two resistors in parallel. One is 15 and the other is 20. Then their equivalence is 35 microfarads. I can calculate the current as 45 divided by 80, which is really here I have the two resistors, they're gonna add to 80. And then this is really the voltage. I'm so sorry, like it seems I'm sick. Thank you.